This is a revision of a talk I gave earlier at CPPCon with similar title, but for non-cryptographers. So that's the main point. Nothing we're talking about today is stuff you should think about if you care about cryptography. And the motivation for this is about audio, but a lot of these things could apply for other situations where you care about random numbers. Again, not when security or cryptography matters. Before we get into things, just want to make sure, just clear, this is a flame war free zone. We're not going to talk about tabs versus spaces or Emacs versus Vim, nor am I going to crown a champion of any random number generators. You can find some very spicy threads on Reddit about some of this stuff. I am not a statistician. I can't tell you what the right answers to those debates are, but I'm just going to tell you about my adventures and conclusions I've come to personally. Just a little bit about myself. I'm a principal software engineer at Soundwide on the audio research team. And Soundwide is a group of companies that's Isotope, Native Instruments, Plugin Alliance, Brainworks, and SoundStax. So most of my experience I'm talking about today comes from working on mixing and mastering software at Isotope. I'm sure a lot of people in the audience are familiar with audio plugins, and just to set a bit of context, a lot of the things that motivated this talk were about the fact that we might run multiple copies of the same audio plugin in a session, and thinking about making sure the random numbers are randomly random between those instances. So a brief outline of what we're going to talk about today. First, why I've been spending my time over the past year thinking about pseudo-random number generators. What is a pseudo-random number generator? A little bit how to use the features in the C++ standard library, downsides of some of the things in the standard library, some thoughts on seeding strategies, and the kind of conclusion on what motivated this talk is looking outside the standard library at other random number generators. So this journey began for me in 2019 when we were developing a new reverb product at Isotope, and this was based on reverb technology with some other improvements and special stuff we added from Exponential Audio, a reverb company we had acquired earlier. And in the exponential audio reverbs, if you had many reverbs in a session, they were actually sharing one global random number generator with the idea that the multi-threading in your session would add more chaos and make things unpredictable. But at Isotope, we make deterministic plugins, so you get consistent bounces and other stuff, so that was not going to work for us. And also, I was not convinced that that's actually a better solution for random number generators, because adding that chaos to it might actually disturb the properties of your random number generator. So I was trying to do a little bit of reading and try to figure out, what's the kind of best way to use random number generators. And initially, that just opened a lot of questions, and that was this exploration of the last year. So this started with me just Googling, well, how do I seed the Mersenne Twister, which is a random number generator that comes in the C++ standard library? And that, searching around the internet, made me realize, oh, I should probably actually be looking outside the standard library for more appropriate solutions. And also, as we'll get into, if you don't know what some of this stuff means, there's going to be an explanation of this, but another feature is not just the random number generator, but how you make a distribution, whether you want uniform -1 to 1 to make white noise, or you want to make some dice roll. I was seeing differing advice about what to do. Timur gave a great talk last year at CPPCon about real-time audio or real-time processes in general and the C++ standard library and how to understand the standard and what things count as real-time safe or not. And there were some conclusions that the random features really are not necessarily appropriate for real-time audio. At the same time, I also saw a great talk from Walter Brown, who gave the advice to do it right no matter what your use case, because even if you think it doesn't matter for you now, maybe your code ends up on a rover on Mars and it matters then. So I had these conflicting opinions that I wasn't sure what to do, talking about it at work, and then it turns out a colleague said, oh, I already found you should use Zoshiro 128+, it's already in our code base, but he had implemented the algorithm in a way that didn't fit with the other pieces in the standard library, which has made it not as comfortable to use or swap out with other algorithms, and that's really why it wasn't taking wide adoption yet in our code base. So just some references, if you want to check out these talks later, I highly recommend it. This talk from Walter Brown is a much more in-depth description of how to use the C++ standard library features. I'm going to briefly cover some of that, but it will, this talk will give you all the details you know if you haven't had experience with this. And this is Timur's talk I was mentioning about real-time programming with the C++ standard library. And it's just a picture of, I don't know, she's probably not coming up too well, but some graphs my colleague made to show me, like, oh yeah, you should just use Zoshiro 128, but I just didn't want to take this. I don't know exactly, this is personal benchmarking tool, what it does, and I wanted to actually kind of understand this stuff better before I came to a conclusion. So my real question is, what do I really care about? Probably performance. I think quality matters, or does any of this stuff matter? And we'll kind of see what I mean by that as we're going. And initially I thought I would take an approach of actually doing listening tests and trying to look at perception to see what actually matters for audio. But I realized that's actually probably not good advice to give in this talk, that all of you in your day job should do a science experiment to decide what piece of code you should use. So I'm taking a different approach where we can kind of explore these tools and just try to gain confidence that we've made the right choice. And I have this quote here about being Portland sure. This is something I heard on a podcast whose compliment by Matt Godbolt and Ben Dean. And Ben Dean, they're talking about testing and the fact that you have to have trust in some levels of your stack. Like you have to trust your CPU works, your OS works, and that your bugs are probably at your layer. And so Portland sure is, he's never been to Portland, Oregon in the US. He has friends that live there. He believes it exists, but he doesn't know it exists. And so for me, that's London Shore. Until this trip, I had a close friend in PM. He tells me London's his favorite city. I believed it was a real place, so I was going after London Shore, and I'm pretty sure now London is real. So what is randomness and a random number generator? Let's do a little interactive thing. I'm going to show you a bunch of coin flips, heads and tails, and if I see a show of hands, whether you think this is a random sequence or a non-random sequence. And I'll tell you what's going on after the fact. So does this look random or not random? Show of hands. I need the participation. Oh, good question. Yes, if you believe this is a random sequence, raise your hand. That's the right way to say it. Okay, thank you. All right, for those online, most people raise their hands. What do you think about this one? Most people. What do you think about this one? Most people. And I think this is the last one. Yeah, most people. So I will, oh, we got one more. Yeah, most people. So to tell you what they actually were, this is not a random sequence. I chose these heads or tail flips. This is a pseudo-random sequence by a random number generator in the C++ standard library. This one was a coin toss. So this is true randomness, and it was tails every time. Back to the standard library again, and another standard library one. So my point here is that human perception is really what matters here, and that to all of us in this room, these seem like random sequences. One was truly random, one was not, and others were pseudo-random. And at the end of the day, we're getting the same result. So that's kind of my thesis, is that human perception for us as audio developers is more important than the statistical properties of the ones and zeros that come out of your random number generator. So what is random? We have kind of a few different categories. Truly random numbers, pseudo-random numbers, and quasi-random numbers. Most of the talk will be about the middle category, but let's just go over what these are. A random number are things like a coin toss, dice rolls, your system random number generators like dev-random, although there's some discussions whether those actually count as random. You can read online about that. I'm not gonna get into that. Measuring atmospheric noise, radioactive decay, and my favorite, lava lamps. This isn't a picture of it, but Silicon Graphics had a truly random number generator where they had a camera pointed at a lava lamp and then would use the pixels of that to generate random numbers. And I'd like to build one of those someday for my random device, because I just think that's really cool. And then quasi-random numbers was something that I saw brought up when I was looking into this. Actually, I think maybe Timur, you might have gotten a question about this at CPPCon. And so what a quasi-random number sequence is something that actually has a predictable pattern, but has some appearance of randomness. So if you've seen this chart, if you look on the left, like that kind of seems random, but as you add more and more points, you see there's a specific pattern. I haven't looked in these in detail yet, because my background as a composer doing musique concrète, I came to the kind of intuition that the human ear is really good at noticing the same exact thing happening twice. And so my intuition tells me that these kind of patterns our ears will pick up very easily. But maybe that's something I'll look into in the future, and if they are interesting for some use cases, maybe there'll be a talk. But our subject today are pseudo-random number generators, which are deterministic algorithms that approximate randomness. So if you run them, you'll get the same results every time, but the sequence themselves are random, and if you run multiple random number generators, you should have decorrelated results. And some use cases for pseudo-random number generators, or I'll call them PRNGs for the talk, are cryptography, slot machines, Monte Carlo and other simulations, machine learning, video games, pinball, graphics, and audio. And I kind of sorted them in this way because I have this guess that, as I said, with human perception and stuff, things near the top, the quality of the statistics matters probably a lot. And as you go down the list, I'm guessing that the quality might not be as important because human perception will kind of cloud our judgment, as we saw in the coin toss example. And I separate out pinball and video games because of the physical nature of pinball. That actually adds enough craziness that the random number generators maybe could be bad. So we'll look at a simple example of what you probably shouldn't do to do random number generators. If we're going to make a function to do a six-sided dice roll, kind of a traditional notion of that would be to call this std_rand function, or from C, modulo by 6 and plus 1. Don't ever do this. It's bad. There's a great talk by STL about all the reasons why you should not do this. I'd recommend checking it out. But basically, it's that std_rand is really low quality, might not actually give you that many bits of randomness, and it is not thread safe. And so in a plugin environment, that's going to give you a bad time. Also, this modulo 6 is actually going to give you a non-fair dice roll because 6 is not a power of 2, but std_rand will return a power of 2. So you'll have some extra numbers left over at the end. An example of that is if we have, actually how we should do this right, is if we have a dice and we want to roll number 1 through 5, and we get a 6 out of our dice, we just keep rolling it until we get a 1 or a 5. But it gets a little tricky if we want a random number 1 through 7 on a six-sided die. How do we end up with 7 ever? There's probably some math for this, and that's where the C++ standard library comes in and gives us some facilities to actually do this correctly. So I'll go over that, and then we'll get into some of the issues with this and looking outside the standard library. So this is what a true fair dice roll function would look like. And I'll kind of explain how this works if you've not seen these facilities in the random header in the C++ standard library. So the first part is this std_random device, and that's going to give you what's supposed to be a true random number from your operating system. And we're using that to provide a seed to the random number generator, in this case, MT19937, which is the Mersenne Twister. And we'll get into problems with that in a minute. We make a distribution, and so this is what's going to take our random number generator and turn its random bit pattern into our 1 to 6 dice roll. And we call that in the bottom by passing the generator to the distribution, and that gives us a dice roll. But we probably want to wrap that up in a function like actually a class. So this is maybe what a class version of this would look like. Notice that I have the distribution as a member. And you don't actually necessarily need to do that because many distributions, some have state, some don't. There might be performance consideration to this. You could make it a static in the function. You could make it just a local in the function. If you want to kind of see comparisons of this kind of stuff, I recommend this talk. I just want a random integer. There's some performance benchmarks on this. I won't get in that. So in my examples, the distributions will always be members, but that's not necessarily necessary or what you need to do. But keep in mind that like a uniform int distribution or a real distribution will always has no state, so you can just create and destroy them. But some of the other distributions, like a Gaussian, actually keep some state, and if you destroy them, you actually won't get the result you want. So that's why in my example, I just assume we'll keep them all as members. And the other thing we want to keep in mind as developers doing software is we might want to have some tests for regressions or other things, and we want predictability in those tests. So we don't necessarily just want to always seed our generator with a completely random number, but we might want to actually be able to repeat this sequence over and over again. So in this modification, you see that we actually will print out what the seed value is, and then that will allow us to have another constructor that will take that seed value so we can run one example, see in the standard out what seed was used, and then we could use that in future runs to make sure we're running the tests with the same results. So, little demo time. Let me switch my screens. And I'm going to show you a few audio examples of kind of uses of random number generators that we'll kind of be talking about throughout this talk. So, oh, that would be dangerous, sorry. White noise is one thing. I think we all know about this. So white noise, you can make a lot of different ways, kind of any distribution. The key thing is you have a random sequence, and the average of that sequence is 0. And that will generate white noise. That can be a Gaussian, uniform, triangle, other shapes. And they kind of have different use cases, but we'll see later that the uniform distribution is probably the easiest one to use and kind of get good results. Another thing I'm going to show is, and these two plugins I'm going to show, keep this in mind because these examples will come back as we get through some of the other tests we'll do later in the talk. So this is a plugin for simulating a vinyl record. And, oh, right, off. Oh, sorry. Sorry about that. That's what we get for doing live demos. And so one of the features of this plugin is the ability to add dust and scratches to the record. And I'll turn that off so you can just hear that. And the way this works is that's essentially picking a bunch, we have a number of samples for dust and scratches. And so we periodically choose which samples we want to use and the time distribution of where those scratches will appear on the record or how often dust should appear. So keep in mind the dust and scratches. That will come back in some later examples. And then the other use case, like I mentioned, which was kind of the motivation for this, is a reverb. So this tail in this reverb, there's some random number, it involves, it's not talking reverb, but the short version is to create that tail, there's a lot of delays. And we introduce some random jitter in those delays. And the reason for that is if you have multiple instances of the reverb, the delay lines could kind of cause buildup and dips in certain frequencies. So if you kind of have randomization going on, that deals with those room modes so you don't have frequency buildup. So that's kind of the other use case we're going to look at in some of the examples is the random number generators to make a reverb tail. And back to the slides. Oh, nope, that's, there we go. So, as I said, I was looking into how to kind of use the standard library right when I was doing this reverb before I saw Teamer's talk and found out about some other problems. But I was initially wondering, how do I even seed the Mersenne Twister correctly? And so I did some searching, and I found two great blogs by two developers of random number generators, Sebastiano Vigna and the Zoshiro family of generators, and the PCG generators from Melissa O'Neill. And we'll talk about those generators in a moment, but there's a lot of actually interesting information on both of those blogs just about how random number generators work and some of the problems with things in the standard library. So one interesting thing using the Mersenne Twister is what was Vigna called the Twitter problem. Oh, actually, I'm sorry, this was on Melissa O'Neill's blog, my mistake. And so in this example, we are taking a random number and we seed it with a random device like we did before, and we want to see, oh, if our result is 7, do something. And this example sometimes actually would never get 7 as a result. And with 13, maybe it worked. And the reason for this is the Mersenne Twister has a huge state you have to initialize. And so with certain initial states with your seed, it might be impossible to get a 7 out as the initial number. So it's actually quite hard to use this way. So you actually shouldn't seed it with one value, but there's this thing in the standard library called seed sequence, and you give it a lot of random numbers. But if you look at Melissa O'Neill's blog, she explains that this actually, seed sequence has a number of deficiencies. And so that's basically my conclusion is this is really hard and I don't want to do this. So to kind of cover briefly the kind of overall downsides of using the Mersenne Twister is it has a really large period, which these are pros that I thought were true. Like this, you're talking about, oh yeah, it's this huge period, 1 to the 19937 minus 1. That's great. Like, so will it be that long before it repeats? But I don't really care about that because if I have 44 1 kilohertz sampling rate going on for a year, that's only 1.3 to the 12 sample. So basically, like this will go like the heat death of the universe before it repeats, and that doesn't really matter for our use cases. I heard it was high quality. Mersenne primes seemed cool, and actually Mersenne also did a lot of early music theory stuff about strings, and I thought that was really cool. But it turns out it's hard to seed. It's quite slow because it has this huge internal state. It periodically needs to reshuffle, which also means it sometimes seems fast and every now and then has to do a giant piece of work and you might drop a buffer. And it turns out it fails a number of recent statistical tests, so it's actually just not even as good as everyone thought it was. So changing gears to seeding strategies, because this is actually what motivated my research into this, is there's a bunch of different ways you can give a random number generator its initial state. So its seed will tell you kind of what its deterministic sequence is. One is the random device that I mentioned before, which would kind of randomly start up. For audio plugins, we don't really want that because we want it to work the same every time you load your session. I mentioned seed sequence, it's hard. Some people use time. Please don't do that because you can actually just very easily end up with two things that you gave the same time and then they're the same and not random. You can give things sequential sequences, one after the other seeds, and that's actually kind of a very easy technique that I'm going to talk about using. And then also some random number generators also have the idea of a jump where you can like give it one seed and then jump way far in the sequence to have two non-overlapping ones, and we'll talk about that a little bit later. But in the case of sequential seeds, imagining I have multiple reverbs in my session on different aux buses, and I might give the first one seed 42, the next one seed 43, the next one that loads seed 44, but then what happens when I reload my session? I want to make sure that they could load in a different order, and like, 44 could actually be the first one that opens up, then the host could load 42 and then 43, and I want to make sure each track actually gets the same random number generator every time. And also make sure that when you reload your session and add a new one, that it actually gets a new seed, so we have no overlapping seeds. So I'm gonna go through these slides very quickly. It's mostly here as a reference for the future, but I made this thing called the seed pod that I use to basically hand out random numbers to each plugin instance. So it has this one function, new seed, that just takes this atomic int that is the next seed and increments it and gives one back to you. So every new instance uses this to get the next seed. And then when you load a plugin, the plugin reload a session, each plugin will claim a seed. And basically what that does is it says, oh, I'm 43. And that means that it will just increment the next seed to 44. And then once everything loads, the next highest number will be the one after that. So I recommend looking at this a little later. I'm happy to answer questions afterwards about it. But this is, I think, a good way to give every plugin in your session a different seed. But as I said, that looking into how to seed things correctly led me to actually discovering there's a lot of other random number generators out there that are quite better than what is in the standard. So I recommend checking out these links. There's the blog about the Zoshiro generators and a C++ library that I found for implementing those, the PCG family generators, and another group that is Random123 and Philox, which is actually, I think, being proposed for the standard. I'm not really sure the latest on that. So the Zoshiro family has a number of different generators that have different sizes and slightly different behaviors, but the kind of optimal ones for the case that we care about are generating floats or other 32-bit values. So the Zoshiro 128 family is the ones that are most interesting for us for audio, and the 128 plus is the one that's good for floats because that has a little bit of not great randomness in the lower bits, but you don't need those for a float because you only need 24 out of the 32 bits available. So that's kind of the intuition is that's the recommended one for audio, and that's what my colleague was already using on some stuff. What I really like about it is it's really easy to seed. If you just give it a single number, that's enough to seed it because it uses this split mix 64, a different random number generator to fill out the state. So that's one property I really liked is the ability to just seed it immediately with one number and you're good to go. The PCG family has two versions, a 32-bit and 64-bit. And And seeding this involves Melissa's kind of improved version of the seed sequence, and has this ability to kind of scramble the seed and give you actually some other properties out of that. And then, like as I mentioned, there's this random 1, 2, 3 group, and the Phylox generators had at one point been proposed as standard. I don't know if that's still active. And these are not actually what you think of as a random number generator, but they're just a stateless function that you pass a seed and a counter to. And these are mostly used in simulations, so you can kind of have one seed and a number of different counters. So like each simulation might be 1, 2, 3, 4 in the counter. So that's not so convenient for me for audio, and it turns out those were a bit slow compared to the others. So I'm not going to look at those too much, but I wanted to mention them since they're proposed as standard. And various other programming languages use all 3 of these generators. I know this one is common in machine learning frameworks for Python. I forget C# and Java use some of the other ones I mentioned, but I forget which languages use which because I'm focused on C++. So some very kind of simple benchmarks. Sorry, they're not kind of too in-depth, but with this M1 Max that I have here, I was making uniform white noise as a benchmark, and see that the Zoshiro, as my colleague said, yes, it's the fastest one on a micro benchmark, so that's the one I assumed I was most interested in. I'm just going to move past the slide, but this is the generator used for white noise in this test if you want to check it out later. It's a Gaussian version. And here's the dust generator we were talking about earlier that you see, if you look at the bottom, uses 2 of these distributions we talked about. One for integers, which is choosing which audio clip is played, and the other for real numbers to choose the time of everything. Similar thing for the scratches. So how do I get to be London sure that I picked the right generator without doing a lot of math? So go back to demo time. So I have a command line tool here that can generate essentially a wave file that shows where the scratches might appear on a record. So can I have a volunteer to give me a seed number? 42, all right, my favorite, thank you. And I'll use the Zoshiro 128 plus, my intuition favorite. I'll generate that one. And then imagining my kind of plugin scenario, I want my next instance of the vinyl simulation for scratches to have a sequential seed of 43. And if I open both of those up and we look at the output of this, the height of these different lines is showing you what scratches, oh, I'm sorry, it's a little bit hard to see, but what scratches were generated. And you see not only are very different samples being picked based on the height, the timings are very different. So these look like believable scratches on records to me, so quality is probably good enough for my use case. But to be really sure, I have another test that we could do, which is and this test is going to sequentially seed the generator over and over again and see how long it takes to have a collision where 2 scratches are at the same time, because that's probably not what we want in our session. So in this case, with this generator and a seed of 42, I can instage it 23 vinyl simulations, and they're all going to have non-overlapping scratches. And it's probably pretty good, because I probably don't need 23 vinyl simulations in one session. If I try sorry about that. You can try the PCG generator for fun. Oh, that one can do 81, but 23 is probably fine for one session. And one other thing to just demonstrate the white noise quality. So I have lots of different white noise with different seeds available. And if we look at Zoshiro white noise, it's Gaussian in this example, we can do, oops. Sorry, normally I thought I had my alert sounds off. I apologize for that. The PCG generator, and we won't need to look at Mersenne Twister because we said that's bad. So if we look at a spectrum analyzer of this, We see the PCG over a 3-minute pop song. It's completely flat white noise. And, oh, I'm sorry, that was Zoshiro. This is PCG. So they both do great at making white noise. If we look at smaller time segments, sorry, I have the wrong selection tool here. Apologies. If you look at a smaller time segment, we see it's not completely flat, but yeah, that looks like believable white noise. And same thing with the Zoshiro. So yeah, I'm London sure the Zoshiro quality is good enough for audio. And so I did have one other thing I wanted to show, which was like regression tests swapping out PRNGs in that Reverb plugin. But I had serious VPN trouble in London, so it didn't quite pop out in time for the talk. If you want to hear them later, find me. Like they may not be ready later, but sad kitty, we don't get to look at Reverb regression test diffs today. So I don't have much time left, so I'm going to kind of briefly go through kind of the thing that got me thinking about this from Timer's talk is like what we actually can get away with in real-time audio, because these distributions that I was recommending you use, according to standard, don't run in constant time, which is not good for audio because we might drop buffers. And so this, again, in this dust generator, you see we have the int and the real distribution. That might be kind of dangerous because we don't know if they'll finish on time, according to the guarantees of the standard. But benchmarking, it looks like if you look, the simple versions are not using the standard library, but kind of a more naive thing that is at the end of the slides if you want to check it out. And you see it does go faster, which that's probably a good sign. But the real thing is we want something that we know is constant time. Oh, I guess that's the old benchmark slide. So what I found is the implementation for generating real numbers with the standard library usually uses this generate canonical to do a 0 and 1 and then create the floating point. And this is going to be constant time for generating floats with a 32-bit input and reals. So the real distribution is something you can, the uniform real distribution, at least looking in Klang's libc++, you can trust that to be constant time. But the uniform int, as our dice roll example, we might need to keep re-rolling the 6 every time we get the 6 if we want 1 through 5. Also, the piecewise linear at the bottom, that also should be constant time, the way it uses the generate canonical. But you want to watch out for some, because like normal distribution is not going to throw away results like the integer one will, but it isn't going to be consistent in time, because it basically what it does is it generates 2 numbers at once is the general algorithm, one on one side of the distribution, one side of the other. So every time you call it, one time is free, the other time has a cost. Maybe that's okay for your use case. And I think this is actually kind of okay to use these, because I haven't actually found at NI or Isotope too many cases where we're doing like an int distribution sample by sample, but that's often something we kind of are pre-calculating and then using later. So in that case, go for it. If not, I have a slide at the end of a kind of faster, simple generator you can use from that benchmark. Trying out Zoshiro 128 versus the Mersenne Twister, I did some benchmarks in our Reverb plugin, and turns out, performance-wise, Zoshiro versus Mersenne Twister or versus the PCG, our benchmark suite showed no differences. And so the conclusion here is, even though random number generators have different performance, in a complicated plugin like a Reverb, that's not what you're spending your time on. So things like Zoshiro versus PCG really doesn't matter. But keep in mind, even though it doesn't show up on a benchmark, using the Mersenne Twister can have this big cost at the end. So my conclusions from this are that maybe none of this matters. Both for perception and performance, I actually couldn't really show that picking one generator or the other made much of a difference. So I recommend use what's most consistent, but still stay away from the Mersenne Twister in the standard. So Zoshiro 128 Plus is the one I find easiest to seed, so that's kind of my personal favorite. Supposedly it's only good for floats and not ints, but as we saw with our vinyl record example, I think it did fine with ints as well if you want to use one for everything, but technically, according to the author, plus plus or star star is better for ints. And stick with the standard library distributions, I think, most of the time, unless you're doing ints in a real-time fashion. The one exception is if you care about cross-platform consistency, because Even though there's kind of standard algorithms, the standard library doesn't make every implementation implemented the same way. So if you truly care about things being the same across platforms, use Boost, or take the open source solution from Microsoft or Clang and just use that in all cases. And just for your reference, this is an example of how you're supposed to actually create a float from the Zoshiro generators, because it has some lower bits you want to throw away. So this is the recommended way to do that, kind of for doubles up top and floats on the bottom. Some asserts that are useful in that thing. And this is my simple generator, which is essentially making a half-open float range, kind of half an inch below and half an inch above to use rounding to get an int generator. So if you do need constant time ints, maybe try something like this with some asserts. And thank you very much. If there's any questions you want to talk about later, you can email me, and happy to answer some questions now.